Alright, in this video we're going to introduce our second simple machine. This one's called the lever. You probably are very familiar with this. It's like a teeter-totter or a seesaw, depending on how you say it. We can have a resistance force, like I have drawn here in yellow. And we have like a board or something balanced on this little blue triangle. And this thing here, so we get our E-lingo correct, this is called the fulcrum. It's kind of our balancing point, the fulcrum, so we know that terminology. And I can come over here and I can apply an effort force, Fe, down on this, and then lift this resistance force up. Okay, if you remember, work is force times displacement. So if I want to figure out the work input, remember I take my effort force times my effort distance, and that has to be parallel to my effort force. So which way am I pushing it? Well, if I apply this force down here, technically this whole board is gonna rotate around that particular point. So if I apply a force down here, and maybe I should have actually kind of angled it in here, probably would be a little bit more better. It's going to cause this, let's do this in yellow, it's going to cause this point right here to rotate all the way around this whole thing. And that was really bad. I knew that was going to be bad. And so that's going to rotate that all the way around there with this right here being the radius of that circle. Okay, so what's going to happen to this side? Well, this side's going to go up, right? If this side's going down right here, then this side's going to go up, and we'll do a different one here. This side's going to go up, and this has a radius from here to there. This side's going to go up like this and go around that way. So how do I figure out the work input right here? Well, it'd be this force right here, this effort force, times the distance that I'm going to apply it. And maybe I apply it one whole spin. I mean, we don't really do that, but we can just take this to work. So I could say I'll go all the way around this outer yellow circle would be my effort distance. Well, what would that be? So work input would equal Fe, whatever the yellow arrow is, times the effort distance. How far is it around the yellow circle? Well, what is the circumference of a circle? Well, it's 2 times pi times r. So it'd be 2 times pi times this distance right here, this radius. What's the work output? Well, the work output would be the resistance force, Fr, times, again, we have another circle, it's just not as big of a circle, the red circle, would be 2 times pi times r. Well, what is r there? Well, r there would be this arm right here. And if you're calculating an efficiency, if you remember efficiency, it's work output over work input, right, times 100. And what would that be? That would be work output would be the resistance force times 2 times pi times this yellow radius here. And let's call this yellow radius here the distance out to the effort force. Let's call it that, the distance out to the effort force. So 2 pi times dE. Oh, I'm sorry. I messed that up. We're doing the resistance force. So it would be this one here, which is fine. We'll call this arm dr. We'll still call that one dE. That's fine. So Fr times 2 pi times dr over the input work, which would be Fe times 2 pi times dE, right? Times 100. And if you do that, you'll notice that 2 pi's cancel out. So what I end up getting, what I'm trying to show you here, is that work work output of a lever can be calculated taking Fe, sorry, I keep messing this up. The work output could be calculated as taking Fr times dr. Now, this is, I don't want you to get confused. It's not, in this case, really work. So because work, when you have work, the force and the displacement has to be parallel. So if I have this resistance force right here, I take it times this displacement, because this is parallel with this displacement is parallel with the force, and that would be the actual work. But you'll notice here that we can still calculate something out here by taking this force times this displacement, and force is in newtons and displacement's in meters, so it would still be called Newton meters, but I wouldn't actually call that joules because that's not actually calculating the exact amount of work. But we can use that arm right there for our calculations. So let's start over here a little bit, because I have a feeling I'm probably starting to confuse you. So let's say I have a lever here, and I have a resistance force here. Resistance force. Okay? What I can do is, I don't have to draw those circles and figure that out every time. This is my pivot point here. I can divide this up into torque arm, is what we call it, because we're applying a torque. Well, this force is going to apply a torque, causing rotation of this lever. So I can have this distance, and I can have this distance. This distance we're going to call the effort distance, because I'm going to apply my effort force here. And this distance out here we're going to call our resistance distance, because that's out to the resistance force. And I can use these distances and these forces to calculate all the things we did with the inclined plane. So if you remember, what's the ideal mechanical advantage? Well, ideal. That means we're going to deal with the distances. So the ideal mechanical advantage of a lever is dE over dr. These equations don't change. Every single simple machine has the same equation. It's just how do you measure these distances? Well, on the lever, you're going to measure from the fulcrum out to wherever you're applying your force, and that's your dE. You're going to measure from the fulcrum out to your resistance force, and that's your dr, and that's how you calculate the ideal mechanical advantage. How do I get the actual mechanical advantage? Well, if you remember, that's now forces, but now it'll be opposite. So it'll be the resistance force over the effort force. Still the same equation. Actual mechanical advantage, we use the forces. How do I get efficiency? Well, I can still do the actual mechanical advantage over the ideal mechanical advantage. Okay? Which would still be Fr times dr over Fe times dE. Still be the same thing. We always take these times 100, by the way. I hope you understand that for efficiencies, percentages. Okay? And I can still figure out an efficiency. But that's how I do it for a lever. So these arms right here, I'm taking this arm times this force, and you'll notice those are perpendicular to each other. So in this case, it's not like the inclined plane. I can't actually call that the amount of work, because it wouldn't be. It's to find out the actual amount of work, you take this force times however far down you're going to push this actual lever. But I can use this radius here, this arm here is called the torque arm. Sometimes, just so we get the lingo correct, this force times this distance is also called, I like to call it torque. Personally, in physics, we call it torque. But sometimes you'll hear it, especially in POE, it's called the moment, calculating the moment. I don't know why they use that, but they do. So this distance times this force is what I call torque, but they might call it the moment. If they ask you about a question about the moment on a test, then you're calculating the torque is all you're doing. So this is the effort torque, or the effort moment, taking this dE times this Fe. And over here, take the dr times the Fr, that's called the resistance torque, or the resistance moment. So the ideal mechanical advantage is the effort torque over the, or the effort displacement over the resistance displacement. And the actual mechanical advantage, to see what's actually happening, you take the resistance force over the effort force, and we still figure out advantages, mechanical advantages for this simple machine. Okay, next video we're going to talk about, there's actually 3 different classes of levers. Levers are a little more complicated than most simple machines, so we'll talk about the 3 classes of levers in the next video.